Chapter 2: Internal Energy, Work, Heat, and Enthalpy. Section 2.6: Isochoric and Isobaric Processes. The first law of thermodynamics states that energy cannot be created or destroyed. Therefore, in a closed system, delta U is equal to Q plus W. The differential form is du equals dq plus dw. So we have a bar through this differential operator d. So is this one, because dq and dw are inexact differentials. dw is negative p external dv. We need to know the information about this p external to calculate work. Although du by itself is an exact differential, both dq and dw are inexact differentials. The sum of two inexact differentials can be an exact differential. When an ideal gas undergoes an isothermal process, du is 0. This is because we have two components to consider: the potential energy of the system and the kinetic energy of the system. Now we have an ideal gas. We're going to assume the potential energy is always 0 for an ideal gas, because there's no attraction nor repulsion between ideal gas particles. Now let's look at the kinetic energy. In an isothermal process, temperature remains constant, and temperature is the measure of the average kinetic energy of all particles. Therefore, if temperature is constant, the kinetic energy should be a constant. Then du is 0. The internal energy of an ideal gas solely depends on temperature. Now, if it's an isothermal process, again we have this equations. dt is 0. Therefore, dke is 0. There's no change in kinetic energy. du is the sum of dpe and dke. P is potential energy, K is kinetic energy. And there's no change in potential energy, there's no change in kinetic energy. Therefore, du is just 0. Later, we'll learn that an isothermal process can be reversible or irreversible. When P external is always equal to P, the process is reversible. When P external is different from P, the process is irreversible. Later, we'll learn that a reversible process does not involve any change in the entropy of the universe. And if a system undergoes an irreversible process, it is irreversible only because this process increases the entropy of the universe. Therefore, it cannot be reversed, because the reversal will violate the second law of thermodynamics. Now in this section 2.6, we will only study the isochoric and isobaric processes. Isochoric means constant volume, isobaric means constant pressure. In an isochoric process, there is no expansion or compression. Therefore, the expansion work is just 0. In an isobaric process, we'll just assume, because the system pressure is a constant, we're going to assume the system pressure is always equal to the constant external pressure. Again, du is equal to dq plus dw, and dw is equal to negative p external dv. Therefore, in the isochoric process, dv is 0 and dw has to be 0. Again, there's no expansion or compression. There is simply no expansion work. Therefore, du is equal to dq. To specify this isochoric condition, we add v in the subscript. So du sub v is equal to dq sub v. This equation means dq under the isochoric condition is equal to dq under isochoric condition. Note here I removed the bar because now this dqv can be integrated given only the initial and final states. Why? It's simple. Look at this equation. U is a state function, so we can always integrate du given the lower and upper limit of the integral. Therefore, we can also integrate this dq sub v. dq by itself is an inexact differential, but now we specify the condition here. It's constant volume. We know the path. We can integrate this dqv, and qv is equivalent to delta u under the constant volume condition. In this equation, we say delta u sub v is equal to q sub v. Note that we put delta in front of u, but not in front of q. This is because, again, u is a state function. Delta u is the change of u. This is the final u minus initial u. But we do not need to add delta in front of q, because q is associated with the entire process. Q is the amount of heat that flows into the system between the initial state and the final state. Q is a transitory property. Q sub v itself accounts for the internal energy change of this system under the constant volume condition. For most substances, within a small or even moderate temperature change, a small temperature change may be a few kelvins, moderate temperature change may be tens of kelvins. Usually Q sub v is proportional to delta T, or approximately proportional to delta T. Well, it does make sense. If you provide more heat to the system under the constant volume condition, you have larger delta T. And this proportionality is called isochoric heat capacity. It's written as C sub V. C sub V denotes isochoric heat capacity. C sub V is dqv over dt. Well, in general chemistry, you probably see C sub V is equal to Q sub V over delta T, the finite change of temperature on the bottom, the finite amount of heat on top. But now we learn the calculus. It's the exact differential here for Q sub V over the exact differential of temperature. Again, dq is inexact, but now with this v, it becomes exact, or behaves like an exact differential. And also, we know dq sub v is du sub v, so we have this partial integral. Delta u over delta t under constant volume condition is c sub v. Alright, we have a bunch of equations here. CVM is simply the isochoric molar heat capacity. You just need to divide the isochoric heat capacity by the number of moles. You'll get this isochoric molar heat capacity. Note that CV is an extensive property, but CVM is intensive. Alright, because if you look at this division, CV is proportional to the amount, N is proportional to the amount. So this proportionality cancels. CVM is usually a constant or approximately constant within a small or even moderate temperature range. Again, from a few kelvins to even tens of kelvins. The temperature dependence of CVM is often negligible unless you have a very large temperature change, and then CVM may have a significant change. Now we're examining the essence of CVM and the values of CVM for a few substances. The value of isochoric molar heat capacity is equal to the amount of heat used to increase the temperature of 1 mole pure substance by 1 Kelvin in an isochoric process. So a few things. This V stands for isochoric, this M stands for molar, and heat capacity is dqv over dt. Therefore, we have to say per unit temperature here. When heat flows into an ensemble of molecules, this just means a bunch of molecules, usually a large number of molecules. Some molecules may be promoted to higher energy level because molecules can have translational motion, rotational motion, and vibrational motion. Then we have translational, rotational, and vibrational energy levels. With enough heat, a molecule may be even promoted to an electronic excited level. For example, if you heat up a molecule, you can even break a bond in the molecule, well, providing high enough temperature. Therefore, the isochoric molar heat capacity includes four components: the translational, rotational, vibrational, and electronic molar heat capacity. The first three terms are referring to the motions of the heavier nuclei of the molecule. For example, if we're talking about a water molecule, it can do translational motion. It just moves in the x, y, and z directions in space in a concerted manner. It can do rotation about its own axis. There are x, y, and z axes that cross at the center of mass of this water molecule. This water molecule may also undergo vibrations. For example, oxygen and hydrogen stretching, and also there's a bending motion. Now we have this electronic term. This is about electrons. This is a little bit more complicated. We need to study quantum chemistry before we get back to this electronic molar heat capacity. But for now, I just want to say this is usually small. Electronic molar heat capacity is usually small because it's very hard to promote a molecule from the lowest electronic energy level to even the second lowest energy level. Alright, again, there are four components. The last two are often negligible because it's hard to promote an electron electronically or even vibrationally. For example, we have a water molecule, it does vibration, and can we somehow promote this water molecule into a higher vibration energy level? Well, the answer is yes, but you need a lot of heat. So this kind of promotion is very unlikely. It's very common to see the translational and rotational promotion. Alright, for atomic gases such as helium and argon, we do not have molecules, we have only atoms. Atoms do not undergo rotation or vibration. So the CVM of atoms is simply the sum of translation and electronic. Alright, so there are only two terms. In a solid or liquid, molecules cannot translate. They cannot rotate freely. So if we have ice, there's no translation, there's no rotation of water molecule. If we have liquid water, there's not much translation at all because each water is surrounded by other water molecules. It's hard for water to kind of move around. They can still rotate, but the rotation is not free rotation. It's called a partial rotation. So the molar heat capacity is the sum of three terms only: partial rotation, vibration, and electronic. And again, usually the last two are negligible. Each translational or rotational motion contributes 0.5 R, or 1/2 of the ideal gas constant, to the CVM of gas at the room temperature. At room temperature, the three-dimensional translational molar heat capacity, isochoric heat capacity of an atom or molecule is 1.5 R. Why? Three dimensions. The molecule can translate in the x, y, and z directions, and in each direction it's 0.5 R. Three directions, 1.5 R. What about the rotational isochoric molar heat capacity? Well, it depends. If you have a non-linear molecule such as water, there are three different rotations. Well, again, you can just find the center of mass for the molecule, and then you can have three axes perpendicular to each other, all crossing the center of mass, and then the molecule can rotate about these three axes. Therefore, there are three different rotational motions. Each rotational motion contributes 0.5 R. Three of them, 1.5 R. But if you have a linear molecule, well, the rotation of such a molecule is considered two-dimensional rotation. Here are examples: HCl, HCN, C2H2. They are linear. There are only two rotational motions. This is only because there are only two rotational axes. The molecular axis that contains all atoms is not considered a rotational axis, because if you try to rotate the molecule about this molecular axis of a linear molecule, well, there's not really any change of the position of the nuclei. Alright, so now if we look at a linear molecule, it can undergo two-dimensional rotations. Therefore, it's a rotational isochoric molar heat capacity is just R. If you have atoms, they do not have rotational motions. They do not have rotational CVM. Over here in this graph, it shows you, well, three different rotational motions of water. Again, you need to somehow find the center of mass. It's right here. And then there's an axis passing through the center and perpendicular to the screen. So you have this kind of rotation. Also, you can have this kind of rotation or this kind of rotation. So for water, its rotational molar heat capacity is 0.5 R times 3. The vibrational CVM is typically much smaller than R, because it's very hard to promote molecules vibrationally. So they do not easily absorb heat and jump to the higher vibrational energy levels. The electronic molar heat capacity is even smaller. So we usually neglect the vibrational and electronic molar heat capacity. But if the temperature is high enough, molecules can be promoted from the lower vibrational energy level to higher vibrational energy level. Well, in this case, the vibrational molar heat capacity can become more significant. And there are also exceptions to electronic molar heat capacity. Occasionally, we have a molecule with some excited states very close to the ground electronic state. Well, we see some transition metal complexes with this kind of feature, and then their electronic molar heat capacity may become significant because just by heating up this kind of molecules, well, electrons can be promoted to the second lowest electronic state. For the argon gas at a typical temperature, for example, room temperature, just even between like 50 Kelvin to 1000 Kelvin, its translational CVM is just 1.5 R. Well, it's just because there are three dimensions, and then 0.5 R times 3 is 1.5 R. Argon atoms do not have any rotational or vibrational motions. We neglect those. Its electronic molar heat capacity, it's negligible. It's very hard to promote an electron in the argon gas to a higher energy level. Therefore, we just predict the numerical value of the molar isochoric heat capacity of argon is 1.5 R. R is 8.3. Roughly 8.3 joule mole Kelvin, so we do the multiplication, we get 12.5. And the experimental value is also 12.5, so a really good agreement here. For nitrogen, more complicated, it's a molecule. So we have to look at the rotation and translation. The translation is still 1.5 R, so just imagine this nitrogen molecule moving in the X, Y, or Z direction in space in a straight line. So 1.5 R for 3 dimensions. It's a linear molecule, so it has only 2 rotational modes. We're going to predict its rotational molar heat capacity is just R. Alright, and then we sum it up. We predict the total molar heat capacity of nitrogen 2 is 2.5 R. Oh, I forgot to mention isochoric. Now R is roughly 8.3. If we do the math, it's going to be 20.8. What's the experimental value at room temperature? 20.6. Good enough. At a very high temperature, well, this value may exceed 2.5 R. Only because at very high temperature, well, it's possible for some nitrogen molecules to be promoted to higher vibrational energy level. Now we have a triatomic gas. It's H2S. hydrogen sulfide. It has a translational molar isochoric molar heat capacity 1.5 R. Because it's nonlinear, we have 3 rotation modes, so the rotational CVM is also 1.5 R. And we're going to just estimate the total CVM is 3R. 3R is roughly 24.9. And then the experimental value is 25.4, so not too bad. If you compare this to, the difference is about 2%, I guess. But still, I just want to say this experimental value is 0.5 higher. Mostly because in H2S, there's some vibrational modes that can be more easily changed. For example, the bending, I think it's just mostly the bending. You have a HSH bond angle, and if you change the bond angle, it's called a bending motion. It's also considered a vibration. And this molecule can bend faster at a higher temperature. That means it absorbs heat and the temperature goes higher. That means we have a little bit molar vibrational heat capacity. It's about 0.5. So that accounts for the difference between our prediction, 3R, and the experimental value. Triatomic and polyatomic molecules sometimes have notably different isochoric molar heat capacity. Another example, SO2, sulfur dioxide. Its literature value is 31.3 joule per mole Kelvin. It's much greater than like 25.4 for this hydrogen sulfide. So both are triatomic. They both are nonlinear. How come this one has a much larger value than this one? Well, it's simply because in SO2, atoms are heavier. So they usually have smaller vibrational energy spacings. It's just a little easier to promote this heavier molecule SO2 from the lowest vibrational energy level to the higher vibrational energy level. We have more vibrational heat capacity, so that's why this is larger. Alright, so yeah, if you have a really heavy molecules with heavy atoms, they may have a larger molar heat capacity. Then lighter ones, over here you have hydrogens, you have hydrogens. Alright, so there are always exceptions. And if you have polyatomic molecules, for example, if you have a large molecule with 50 atoms, and there are approximately 144 vibration modes. So even if each vibration mode contributes a very little amount molar heat capacity, and if you add up 144 such vibration modes, it can still be significant, and they still have a larger isochoric molar heat capacity than those smaller molecules. In summary, at room temperature, atomic gases have a CVM of 1.5 R, only because they have only 3 translational modes. The atomic molecules usually 2.5 R because we have 3 translational modes and 2 rotational modes. Now if you have a linear triatomic or linear polyatomic molecules, well, it's just 2.5 R plus their vibrational CVM. It's very often small, but again, if you have really heavy atoms, this can become larger. If you have many atoms and therefore many vibrational modes, you might have larger CVM. What about the CVM of non-linear triatomic and polyatomic molecules? Well, it's going to be 3R at least. Why 3R? 3 translation, 3 rotations. Together, you have 0.5 R times 6, you get 3R. And then we need to take this into account. The vibrational isochoric molar heat capacity. It depends on the situation. Again, if you have heavy atoms in the molecule, or if you have many atoms, and then its CVM might be significantly greater than 3R. Later in section 2.9, we can prove CPM is simply CVM plus R for ideal gases. What is this CPM? It's actually isobaric molar heat capacity. It's different from isochoric molar heat capacity. What does that mean? It tells you if we heat up a substance, and increase its temperature by 1 Kelvin, actually we cannot compute the amount of heat unless we know the condition. For example, it can be isochoric, it can be isobaric, and they actually differ by R if your substance is an ideal gas. Alright? For real gases, well, this equation holds approximately CPM is approximately CVM plus R. For a liquid or a solid, never use this equation. Again, this equation is for ideal gases exactly, and for real gases approximately. This equation is almost never correct for a liquid or a solid. Okay, even if it's correct, it's just coincidence. Okay, now for a liquid or solid, well, it can be as small as 0. For water at 4 degrees Celsius, CPM is equal to CVM. Okay, that's mind-boggling already. And then for some other liquid like benzene, the difference can be as large as 5R. But in the end, CPM can never be less than CVM. I wrote a paper on this topic because I saw in several PChem textbooks they've got a wrong statement. They ask students about under what conditions CPM can be less than CVM, and usually they use water at for example 1 degree Celsius as the example. Okay, that's actually wrong. For water at 1 degree Celsius, CPM is still greater than CVM. So I wrote a paper on this and published the paper in ACS Omega, and you can click this website to see the proof. And also you can just search for my papers. For example, can CPM be less than CVM? And you probably will find this paper. Over here we have a table of the isochoric molar capacity of selected gases at 15 degrees Celsius and 1 atm. This is not 25 degrees Celsius, but as I mentioned, isochoric molar heat capacity is roughly constant within a small or even moderate temperature range. So between 15 and 25 degrees Celsius, those numbers are pretty much just the same. Now let's look at monatomic gases, argon and helium. The CVM is just 12.5 R. It's just 12.5 joule per mole Kelvin. It's just 1.5 R. From the 3 translational modes, diatomic, you have the values here, and you have the values of molar heat capacity divided by R. It's roughly 2.5. Okay, from this 2.49, 2.45, all the way to here 2.8. If you look at chlorine, chlorine is 2.98, a bit more than 2.5. Why is that? Chlorine atoms are just heavier, than all those other atoms. When you have heavy atoms, the vibrational energy spacings are small, so it's actually a little easier to heat up chlorine gas, so that these chlorine molecules can occupy some higher vibrational energy levels. Therefore, vibrationally, chlorine may absorb some heat. Therefore, I think the difference between 2.98 and 2.5 R, well, usually it's just vibrational of chlorine too. Triatomic, again, there are 2 different triatomic molecules, linear versus nonlinear. I think CO2 is linear, and then if it's linear, it should be what? It should be 2.5 R. But over here we have 3.4 R. This is because, look, we have CO2, carbon dioxide. There are actually 2 bending motions. The carbon-oxygen bond angle is, well, supposed to be 180 degrees, but if you heat it up, CO2, a linear CO2 may undergo like bending motions, and the CO2 molecules can absorb heat to speed up the bending motion. So it needs to kind of absorb more heat. Therefore, this is more than 2.5 R. Now let's look at some nonlinear molecule like H2S, hydrogen sulfide. It's about 3R, a bit more than 3R. This is nonlinear, so we have 3 translations, 3 rotations. Our prediction is just 3R. And why 3.06? Well, just a little bit from vibration. And we mentioned SO2, a lot more than 3, N2O, significantly more than 3. Alright, what about CS2, carbon disulfide? I think this is much greater than 2.5 because of the very small vibrational spacing. I think I didn't do the actual calculations for this molecule, but this is just a very large number actually. So that usually tells you this molecule has very small vibrational energy spacing. Alright, now get back to this equation. du is dq plus dw, and dw is negative p external dv. We're going to use this equation and this equation to analyze an isobaric process. In an isobaric process, dp is 0, there's no change in pressure. It actually indicates P external is equal to P, because if it's different, if P external is greater than P, well, the system pressure will change until it increases to P external. If P external is smaller than P, and the system, I think, will just expand until its pressure decreases until it reaches this low level. Therefore, for an isobaric process, usually we just assume P external is equal to P. Alright, and then it's easier for us to get the expression for work actually, because dW is negative P external dV, and we can replace P external with P. So dW is negative P dV, and du is just negative P dV plus dq. And also this dq can be rewritten as dqp now, because we know the pressure is constant. It's an isobaric process. dq itself is an inexact differential, but if we know it's isobaric, we can actually integrate dq now. This becomes exact differential. Alright, now to specify the isobaric condition, du sub p is negative p dv plus dq sub p. And we have this equation. dq sub p is du sub p plus p dv. We just move this p dv to the left hand side. Because pressure is constant, so we can move this p back into the differential. So it's du sub pressure plus dpv sub pressure. Alright, and we can actually sum up u and pv. So this two, remember dx plus dy is just the exact differential of x plus y. So you can do the same thing here. It's just the exact differential of the sum here under constant barrier condition, u plus pv. So it's neat. You know, if we have isobaric condition, the change of u plus pv is simply the amount of heat. Alright? For convenience, you know, we just define enthalpy H to be u plus pv, because if you measure the amount of heat under isobaric condition, let's say you get like 5 joules, you can say, well, the change of u plus pv is 5 joule. Or you can say the change of H is 5 joule. You know, the latter is more convenient. You don't have to say, well, the change of internal energy plus the product of P and V is 5 joule. You just say the change of enthalpy is 5 joule. And backward is more convenient. For a chemical reaction, if you know the enthalpy of the products and the enthalpy of reactants, you take the difference, you know how much heat can be released or absorbed by this reaction under constant barrier condition easily. Right? So you just need to know those enthalpy values. Or you can know, well, what's U and then what's PV for the chemicals, and then you can still do the calculation, but it's less convenient. Alright, again, for convenience, we define H to be U plus PV, and D sub dQp is DHP. And QP is just delta H under constant barrier condition. So that's neat. And also under isobaric condition, for most substances within a small or even moderate temperature change, so a few kelvins or even tens of kelvins. Q sub P is proportional to delta T as well, so we have some proportionality. It's called isobaric heat capacity. C sub P is just dQp over dt, and because dQp is equal to dHp, again the change of enthalpy is equal to the amount of heat for the isobaric process, we can write Cp is delta H over delta T under constant pressure. CPM is just Cp over N. It's isobaric molar heat capacity. Cp is extensive, CPM is intensive. CPM does not depend on the amount of the substance. The temperature dependence of CPM is often negligible within a small or moderate temperature range. They may differ by, for example, 1% if the temperature changes by 10 Kelvin. So 1% is often considered negligible in thermodynamics unless you need a really accurate data. For ideal gases, CPM is equal to CPM is equal to CVM plus R. For real gases, we still have this equation, but well, this equation holds approximately. Again, for liquids and solids, never use this equation. Alright, for a liquid or a solid, the difference between CPM and CVM can be as small as 0 for water at 4 degrees Celsius, and it can be as large as 5R for benzene, liquid benzene, under certain conditions. But in the end, CPM can never be less than CVM. Now we'll look at two numerical examples. One is isochoric, one is isobaric. In these two examples, we will calculate delta H, delta U, Q, and W. Alright, so example problem 2.6.1. Calculate delta U, delta H, Q, and W when the temperature of 0.2 mole argon increases from 20 to 40 degrees Celsius in an isochoric process. The CVM of argon is given. Alright, so if it's isochoric and we know CVM, well, it's easy to compute Q sub V. Alright, we'll do that. And again, CPM is equal to CVM plus R because we assume this is ideal gas. Now for an isochoric process, there's no volume change. dW is negative P, external dV is 0. So work is 0. So whenever you see an isochoric process, the first thing is you write down dV is 0 and also work is 0. There's no expansion or compression work. And therefore du sub V is dQ sub V, and dQ sub V is just CV dt. This is the definition of heat capacity. Alright, for the isochoric condition. Now we can integrate both sides. Delta U sub V is Q sub V is integral of CV dt. CV is N times CVM. We plug in all the numbers, we get 50 joule. How do we get delta H? H is U plus PV, so delta H is delta U plus delta PV. We know delta U is 50 joule. Now we calculate delta PV. It's an ideal gas. So delta PV is delta nRT. And how do we get delta nRT? Well, plug in numbers. We get delta H is 83 joule. So these two numbers differ. Alright, because actually PV changes. This PV changes. Why does this PV change? Does this PV change? Because the temperature changes. When the temperature changes, nRT changes, and PV is equal to nRT. Although this is not an isobaric process, but we can still compute delta H by integrating Cp dt directly. How is that possible? Because, again, this is ideal gas. For ideal gas, H only depends on temperature. And why is that? We mentioned U only depends on temperature for ideal gas. H and U differ by PV or nRT. Alright? And it's an ideal gas, right? So, and U depends only on temperature, and then PV is equal to nRT, which only depends on temperature. So we conclude H only depends on temperature, right? And then delta H is simply over here, we just look at the temperature change. We get 83 joules. So these two calculations are both correct. And also we can imagine this. Let's somehow change the state of the system. in the isochoric process that consists of two steps, we can do isobaric first and then do isothermal. Alright, so if you look at the initial state and the final state, okay, from 20 degrees Celsius to 40 degrees Celsius, and it's isochoric. From V initial to V initial, that's isochoric. But because enthalpy is a state function, I can break down this isochoric process into two steps. First isobaric and then isothermal. In the isobaric process, I hold the pressure constant. Only the temperature changes. So obviously we can use this equation. Delta H is Q sub P and then its integral of Cp dt. What about isothermal process? We know for the ideal gas, H only depends on temperature. And there's no change in temperature. Therefore delta H is 0. So we can sum up the change in enthalpy in these two steps. The result is just the integral of Cp dt. That's why we can just use this equation. Delta H is the integral of Cp dt directly, even though it's not an isobaric process. Again, my argument is simple. It's not isobaric, but I can break down this isochoric process into two steps. One step is isobaric, so I can use this equation. In the other step, delta H is 0 anyways. Now example problem 2.6.2. Calculate delta H, delta U, Q, and W. In an isobaric process, the temperature changes from 20 to 40. The CVM is 1.5 R, the CPM is CVM plus R. Because it's isobaric, dP is 0, we have dQp is equal to dHp, so we integrate both sides, plugging all the numbers, we get 83 joules. Delta U is delta H minus delta PV, and delta PV is just delta nRT. And we know the temperature change, we know delta H, we get 50 joules for delta U. Alright, how about work? Work is delta U minus Q. Delta U is 50, and in this isobaric process, Q is not 0. Alright, Q actually is 83. So we get W is negative 33. It's negative. That means the system expands and does work to its surroundings. Alright, so if you look at these two numbers, 50 and 83, these two numbers, 50 and 83, well, it's just because the system is an ideal gas, and for the ideal gas, U and H only depend on temperature. And if we look at the temperature, it's from 20 to 40. Over here it's 20 to 40 in this isochoric process, 20 to 40 to the isobaric process. And because U and H only depends on temperature, so whether it's isochoric or isobaric, we'll get the same values for U and H. However, we get different values for Q and W. Alright? In the previous example, it's isochoric, W is simply 0. Over here, W is negative 33. Why is that? Q and W are path functions, and Q and W really depend on the process. So even if delta U and delta H are the same between these two examples, Q and W can be different. Again, I want to emphasize the definition of enthalpy. Enthalpy is U plus PV. For an ideal gas, you can rewrite PV to nRT. Alright, only for ideal gas. For PV, for a real gas, PV is approximately nRT. For a liquid or solid, never write PV equals nRT. Again, Q is a path function. When the process is isochoric, USdQ is equal to CVdt. Okay, for isochoric process. What if the condition is isobaric? If it's isobaric, dQ is Cp dt. Alright, and Cp and Cv are often different. They are almost always different. Cp is almost always greater than Cv.